Alright, let's go ahead and get started on this problem. It's a long problem and it'll take us a while to solve, but we have a geothermal heat pump operating at steady state with refrigerant 134a as the working fluid, and the condenser heating is 10 kilowatts. So if we take a look, we have components of a compressor, condenser, expansion valve, evaporator. So the refrigerant 134a is flowing through those four components, and the heat output of the condenser is 10 kilowatts, and that 10 kilowatts is used to heat up the air that is the house air. So it's return air from the house coming back at 20 degrees C. It's being heated to 40 degrees C, and that's what's being supplied to different parts of the house to keep it warm in the winter. Okay, the heat pump uses water from geothermal wells as the thermal source. So here we have in the evaporator water, supply water, and return well water. So the supply well water is 12 degrees C, and then it's returned at 9 degrees C. All right. And then operating data is shown in the illustration. So we're given for state 1 the refrigerant temperature and pressure, and at state 2 the refrigerant temperature and pressure, and likewise at state 3 the temperature and pressure, and then the pressure at state 4. They also give us a temperature entropy diagram, a TS diagram, and we see that state 1 is shown to be slightly superheated, and then at state 2 and 2s, so that we have some isentropic efficiency for this compressor, or there are some irreversibilities in the compressor. That's why we have state 2, 2s. And then state 3 is showing it to be slightly subcooled liquid. And then state 4, it's irreversible expansion through the expansion valve down to some quality at state 4. Okay. What we can see is that the pressure is 9.2 bar. So this is 9.2 bar. That's the condenser pressure for the refrigerant 134a. And at 9.2 bar, the temperature, Tsat, is around 36.3 degrees C. So it's coming out at state 3 at 30 degrees C. So it's coming out about 6 degrees C subcooled liquid. Okay, and then down here we see that the pressure is 2.3 bar, 2.3 bar. So 2.3 bar is the lower pressure, or the evaporator pressure, and its saturation temperature is negative 6.55 degrees C. And so it's coming out at state 1 at a temperature of 1 degree C. So it's superheated by about 7 degrees C. What is that? 7.5, 7.6 degrees C. From negative 6.5 up to 1 degree C. All right. Now, the compressor is assumed to be adiabatic, meaning there's negligible heat transfer between the surroundings and the compressor. So just only is energy transfer is this shaft power coming in. Now there's quite a few components that they want us to solve for. Let's go to the next slide. So this figure is going to be repeated, it's not changed, but what we see is there's a bunch of parts, and we don't want to get overwhelmed with too many parts. We just want to take one part at a time. Solve for the volumetric flow rate of the heated air that goes to the house. So what is this? AV of the supply air. That's for part A. The isentropic compressor efficiency. So get that efficiency of the compressor. The compressor power. Get this W dot. of the compressor, the coefficient of performance, COP, of this heat pump system, and then the volumetric flow rate of water from the geothermal well. And this volumetric flow rate, different symbols can be used. Let's just use AV of the well water in liters per second. And then the last, a full Exergy accounting for the system. So Exergy calculations, and then devise and evaluate a second law efficiency for that heat pump, which the answers are given here for all these parts. But let's take one at a time. So the illustration will be repeated as well as a TS diagram, but all the other information has been removed, and now we're just focused on determine part A. What is that volumetric flow rate of heated air to the house? Well, we'll take a look if we just do analysis from the perspective of the air. Right here we have a control volume. We know we have 10 kilowatts of heat coming in from the condenser, from the refrigerant that's condensing. And so that just is going to be heating. So one mass flow rate in, one mass flow rate out, just of the supply air. And so what we find is that the Q dot from the condenser to 10 kilowatts is equal to the mass flow rate of the air times the enthalpy change, enthalpy exit minus enthalpy inlet for the air. And the standard assumption with lacking more information is just use a specific heat. So mass flow rate of the air, the specific heat, constant pressure, C sub P of air. Then you have the temperature exit minus the temperature inlet of the air. And so we can look up the specific heat for air, and it's around, let's say, 30 degrees C. You can try to get it more accurately, but it's going to be real close to 1.005 kilojoules per kilogram Kelvin. Okay, so it's like we've got the specific heat, we have the two temperatures in and out, and we know that the heating rate from the condenser. Okay, so we solve for the mass flow rate of the air, Q dot, divided by C sub P, temperature exit minus temperature inlet. And the mass flow rate of the air comes in at 0.4975 kilograms of air per second. Then we recall that the mass flow rate of air is equal to the volumetric flow rate of air times, or divided by, the specific volume of the air. And the specific volume of the air is given by the ideal gas equation. And now it's also, if you read the question, you say, which one is it? Is it the specific, do they want the volumetric flow rate of the return air or the supply air? And the volumetric flow rate of the heated air that's going to the house, I would assume that's the supply air. So this would be of the, if you wanted to add supply air. It'll be slightly different than the volumetric flow rate of the return air, just because of the temperature difference and the density difference. But we use ideal gas equation, and we have that this is RT of the supply air that's exiting right there, divided by the pressure. Now, we don't know any information about the pressure other than we would just assume it's atmospheric pressure. Okay, so let's go ahead and calculate that specific volume of the supply air. It'd be 8.314 divided by 28.97. That's going to be R for air. Then the temperature, it'll be the 40 plus 273 converted to Kelvin. And then the atmospheric pressure, 101.3 kilopascal. And you can calculate some exiting specific volume about 0.8867 meter cubed per kilogram for that supply air. Okay, So the volumetric flow rate of the supply air is just that mass flow rate times that specific volume of the air. Okay, and so we have the mass flow rate of the air calculated right here. We have the specific volume, and you calculate the volumetric flow rate of the supply air, and it comes in at 0.4412, too many digits, but there you go, meter cubed per second. There you go. All right, let's go to part B. All right, what is the isentropic compressor efficiency? Well, the isentropic compressor efficiency would be the specific work of the compressor if it would be isentropic compared to the specific work of the compressor actual. Okay, and we're given this information about the temperature 1, pressure 1, and temperature 2, pressure 2. So I like to construct a table of the properties to help organize the information. So I would introduce states like 1, they've already introduced it, and then 2, assuming it's isentropic, the 2 actual, which is based on the temperature and pressure they give us, state 3 and state 4, and then I like to put pressure in kPa or bar, the temperature in degrees C. Some quality would be for state 4. That's where the quality is needed or used to check things. And then the enthalpy in kilojoules per kilogram and the entropy in kilojoules per kilogram Kelvin. And there's one other property, but I didn't leave enough room. Maybe I'll do this. I'll scoot this down if I can grab it. I'll just scoot these down a little bit. And then what I'll do is I'll put state 0 right here, and then 1. So this is the dead state. Okay, and then if you did the dead state, you could put the flow exergy E sub F in kilojoules per kilogram. It looks like I ran out of room. But we can fill out this table. Let's do it with the information given. So the dead state in kilopascal would be like 101.3, or depending what, if we look right here, it is given to be 1 atm, so that would be the right dead state. And and then the temperature, dead state temperature is negative 10 degrees C. All right. Okay, you can go ahead and get the enthalpy and the entropy, and the flow exergy is going to be 0 at the dead state. Okay, then, and this is going to be superheated, a little note, superheated vapor. Okay, state 1, what is the pressure at state 1? 230 kPa. And what's the temperature? 1. And we can get the enthalpy, it's going to be 250.08. And the entropy, 0.9477. And the flow exergy is 16.987, too many digits, but there we go. All right, how do we get the flow exergy? Well, we've done that before. It's just E sub F is going to be the enthalpy at state 1. So let's say we're calculating the flow exergy at state 1. It'll be enthalpy 1 minus the enthalpy at the dead state, which I didn't write up here, but if you evaluate it, it comes in real close to 244.7, and entropy is 0.9918. Okay, minus the dead state temperature. So the dead state temperature is negative 10. We convert that to 263 Kelvin, so T naught. Okay, times S1 minus S naught. So you have all the information. Let me just show you right here. Here's enthalpy 1. Here's dead state enthalpy, the dead state temperature, the entropy, and the dead state entropy allows you to calculate the flow exergy at 1. Okay, let's continue on. So if you assume isentropic compression, then this the pressure is boosted up to 920 kPa or 9.2 bar, and the entropy is 0.9477. You would then need to, it's superheated vapor. You're given basically the pressure and the entropy. Calculate the temperature if you want it, and calculate the enthalpy. The enthalpy is the property we really want. This comes in at 279.96. Yes, interpolation, but oh well. And then if you wanted to, just for kicks, we put in the temperature would be 48 degrees C. It comes in. All right. Now it actually comes out of the compressor at not 48 degrees C, but 54 degrees C. That's why they're showing an increase in temperature right there. So instead of coming out at 48, it comes out at 54. So that's what's that, 6 degrees higher. Okay, now evaluate the properties, superheated, knowing the pressure and the temperature. Okay, so you can evaluate H, knowing the pressure and the temperature. That's 286.28, and the entropy 0.9672. You can also get the flow exergies. Let me just write it down here. This would be 46.867 and then 48.064. Looking back at it, I think I did this. I think I just put 100 kilopascal. So change this problem to be 100 kPa if you're trying to reproduce this. Okay. Now, state 3, that's coming out subcooled liquid, as we discussed. So it's coming out at the 920 and 30 degrees C. And so this is H of F, the saturated liquid enthalpy at 30 degrees C. That comes in at 91.49, and entropy 0.3396, and the flow exergy 18.319. All right, and then we go through the expansion valve from 3 to 4. So I should have put down, this is saturated liquid, or not even saturated liquid, compressed liquid or subcooled liquid, compressed liquid, and you know the temperature. Okay, at state 4, it's going to be two-phase, and we know the pressure and the enthalpy. So it drops down to 230 kilopascal, and the enthalpy is 91.49, constant H through that expansion valve. That allows us to calculate the quality. The quality comes in at 0.248, about 25% is already vapor. And the temperature will be the saturation temperature of negative 6.55. And if you want, you can calculate the entropy, which is 0.3531, and the flow exergy of 14.767. All right, that takes us a while, but if you compute the table in one place, it helps organize the information, and it's a lot better. All right, I should have put here superheated, knowing the pressure and the temperature. What is the work that the compressor would need if it was isentropic compression? Well, that's going to be the enthalpy at 2s minus the enthalpy at 1. What about the actual work? Enthalpy to actual minus enthalpy at 1. And so for this problem, the enthalpy 2s is right here. I got too many red check marks, but it'll be 279.96 minus the enthalpy at state 1, 250.08, and then actual enthalpy at state 2, 286.28 minus the same enthalpy 1, 250.08, and we calculate the compressor isentropic efficiency comes in at 82.54%. And I would get rid of the last digit, maybe only report it to 2 significant digits. 3 seems a little excessive, but there you are. Okay, that was a lot of work for part B. I'm going to note that we have the flow exergies available to us, as well as any and all of these enthalpies if we need them for part C, D, E, etc. Let's continue on. All right, so what is the compressor power? What is this W dot C? So W dot C would be the mass flow rate of that refrigerant going through the compressor times the work compressor actual, which is the lowercase w, or the mass flow rate of the refrigerant, times the enthalpy leaving state 2 minus enthalpy inlet state 1. Okay, well, didn't we already solve for the mass flow rate of the refrigerant? Or did we? I need to come back here and look. Well, you're given that it's 10 kilowatts of heat transfer from the refrigerant, and we did not actually, we solved for the mass flow rate of the air, but not the mass flow rate of the refrigerant using this information of 10 kilowatts. So let's do that. So to get the mass flow rate of the refrigerant, we focus on the condenser, little control volume right here. We know it's coming out 10 kilowatts, so the Q dot coming out of the refrigerant in the condenser is the mass flow rate of the refrigerant through the condenser times it comes in with a high enthalpy 2 and exits at low enthalpy 3. And in this equation, that's 10 kilowatts, and we got the 2 enthalpies on the previous slide, H2 and H3 right there. So we go ahead and calculate the mass flow rate of the refrigerant. Comes in at 0.05134 kilograms per second. Then we can use that. Now, knowing the 2 enthalpies, we can calculate the power W dot needed to run the compressor. Comes in at 1.858 kW. Okay. Knock it down to 3 significant digits, 1.86 kW. All right, let's take a look now at part D. So part D says, or asks, what is the coefficient of performance? So the COP for a heat pump system is what you want to accomplish over what it costs to run. So this is what you want over what it costs to run. And we look at it, what we wanted, with a lot of Q dot in the condenser going to the air to heat the air in the house. And what does it cost to run? W dot supply. And we just said, hey, that's going to be 10 kilowatts. And the power to run the condenser, we just calculated to be 1.8583. So the COP of the heat pump comes in at 5.381. So 5.38. So if this was only electric resistive heating, you would have a COP of 1. But here you're getting 5 times more heat into the house for the same amount of electricity you're purchasing. So that's pretty good. All right, let's go to part E. What is that volumetric flow rate of water from the geothermal well in liters per second? So we focus on this m dot of the water going like that. It's interesting that they didn't ask for the mass flow rate. But what is the density of water? Well, somebody says it's 1,000 kilograms per meter cubed, but isn't that the same as 1 kilogram per liter? Yeah. And so basically, if you just calculate the flow rate in kilograms per second, then multiply by the density of water, or divide by it, of 1 kilogram per liter, you'll get the numerically the same value, but it'll be in units of liter per second. Now, if you want to get more precise and say, oh no, it's not 1,000, it's 980 or 970, well then yeah, but you're going to change the answer just a little bit. So what we need to calculate is the mass flow rate of the water. And so you're looking at it and saying, well, I know the enthalpies at 4 and 1, and I know the refrigerant mass flow rate. And so we do an energy balance for the evaporator. And so let me just write it over here, that we'll have the mass flow rate of the refrigerant, and it'll be the enthalpy 1 minus the enthalpy 4. That's like what is the heat input out of the well water and into the refrigerant. And so it's the mass flow rate of the well water times, and now if you knew the change in enthalpy, but we're going to not just do a change in enthalpy, we'll use the specific heat of the water. And because it's water, you don't need to put C sub P, you can just use C for the water. It's like C sub P is equal to C sub V. It's just one specific heat. Drop the subscript for an incompressible substance like water. And then we multiply by, you're coming in with the high temperature and you're exiting with the low temperature for the well water. Okay, so it's like we know these two temperatures. You're coming in at 12, leaving at 9. The specific heat of water, about 4.18 or 4.2. And what did I use for this problem? Specific heat of water, I used 4.2 kilojoules per kilogram Kelvin. Let's grab that out of one of the tables in the back of the book. It's table A19 in our textbook. All right. So that's done. The mass flow rate of the refrigerant and these two enthalpies we know. The only thing we don't know is the mass flow rate of the water. And so the mass flow rate of water equal to m dot refrigerant H1 minus H4 divided by specific heat of the water, and then the temperature in minus temperature exit of the water. And when you compute that, the mass flow rate of the water is 0.6462 kilogram per second. And then if 1 kilogram occupies a space of 1 liter, then the volumetric flow rate of the water is 0.646 liters per second. All right. Now the last part, and it's the long part. They want to do a full Exergy accounting for this system and use the dead state temperature of negative 10 degrees C, which we convert to 263 Kelvin. All right. So what do we have? We have some flow of Exergy coming into the system. So let's do all of our ends. We have the, let's do Exergy flow with the power. So maybe some notation like that. And so we calculated this shaft power coming in to be 1.858 kW. All right. So what is the rate of Exergy transfer with that shaft power driving the compressor? Well, it's 1.858 kilowatts. Okay. Where else could it come into the system? Well, even though we're not trying to get power or work out of the well water, we're just trying to get heat out of it, you can still do an exergy calculation for that. So what do we have? We have the rate of exergy transfer coming out of the water. Let me do this, water. The well water. All right. How would we calculate that? Well, we have the mass flow rate of the water. We just calculated that. And if we could get the change in the flow exergy, it comes in high and leaves at low. So inlet and exit flow exergies for that water. All right. So mass flow rate of the water. How do I calculate the change in the flow exergy? Well, it would be like the enthalpy in minus the enthalpy exit minus T naught entropy in minus entropy exit. All looks good. And then we say, well, we're using constant specific heats and we're treating that well water as if it's a liquid incompressible. So we have the mass flow rate of the water times the specific heat times the temperature in minus the temperature exit. That specific heat, 4.2 kilojoules per kilogram Kelvin, minus the dead state temperature, right there it is, 263. And then what about the change in entropy from inlet to exit? Well, that'll be the same C, specific heat, 4.2 kilojoules per kilogram Kelvin, multiplied by the natural log of the ratio of the temperature. You're doing a in divided by the temperature exit, just like that. All right, just if you had a S2 minus S1, it would be C natural log of T2 over T1. Just make sure that this one pairs up, and then this subscript pairs up. That's all. So even though inlet minus the exit, some people may want to put the temperature exit divided by temperature inlet, but don't do that. This is the correct. So we have 4.2. We have to convert our inlet and exit temperatures so it comes in at 12 or 285 Kelvin, leaves at 9 or 282 Kelvin. So either one, you can put C or K here, but definitely over here you have to put the inlet temperature in Kelvin and the exit temperature in Kelvin. And this is the dead state, forgot my subscript, of 263. So all of those pieces of the pie are known, and I'm just going to say that we can compute that you're getting out of the fluid stream a rate of exergy transfer into the system of 0.589 kW. So 1.858 coming in, shaft power, and then 0.589 kilowatts coming in from the geothermal water. You might think that this is free because you're just getting it out. You're just getting out of the warm earth from the geothermal well. This one you're going to have to purchase from the electric supply company. All right, so those are the ends. If we sum them up, then we have the sum of the ends is equal to 2.447 kilowatts. That rate of exergy transfer has to go somewhere. Okay, where will it go? Well, we're going to have a exergy increase in the air. So on the outs, the first one is what is that rate of exergy transfer into the air? And the way you calculate is just like the way you calculated for the water. You just have the mass flow rate of the air times the change in the flow exergies. So it comes, it's exiting at higher flow exergy than it came in for the air. All right. And this is the mass flow rate of the air times, you're going to have, just like for water, you don't have any pressure change. So you're just going to use the C sub P for the change in enthalpy, C sub P of the air, times the temperature exit minus temperature inlet. And then you're going to have minus the dead state temperature, C sub P natural log of the temperature exit divided by the temperature inlet. And there you go. It's very analogous to what's happening with the water. Because there's no pressure change, the natural log of P exit over P inlet, that's a natural log of 1, is 0, so that drops out. Okay. We need to calculate the 40 degrees C is 313 Kelvin, and the 20 degrees C is 293 Kelvin. We have all of our temperatures in Kelvin, we have our mass flow rate of air, and we can calculate that the Exergy transfer is 1.317 kilowatts being taken out with the air. So you put in almost 2.5, and you took out 1.3. Okay, well, what's the other difference? All being destroyed. So what we have is destruction is an out. Okay, so we have the destruction in each of these components. You can do compressor, you can do condenser, you can do expansion valve, and you can do evaporator. All right, so probably easiest is the compressor. So we just take a look at the compressor. We do a control volume, and then you do an exergy balance for that control volume. And we did already calculate the flow exergy at 1, the flow exergy at 2. So basically for the compressor, we have what comes in, W dot C coming in. It goes into the mass flow rate of the refrigerant times the increase in the flow exergy, EF2 minus EF1, or it's also destroyed. The rate of exergy destruction in the compressor. So it's like we know this, we have these from our tables, and the only unknown is that exergy destruction rate in the compressor. And I'm going to fight for space here, and I'm just going to say that exergy destruction rate in the compressor turns out to be 0.263 kW. All right. How about for the condenser? You do the same thing. You basically make a control volume which has 2 inlet and 2 outlet streams. So the control volume includes the air, and it includes the refrigerant. And boy, I'm running out of room. Let me introduce a clean page. Insert new page. So we do a exergy balance, and what do we have is we have the mass flow rate times of the refrigerant times the EF of the refrigerant flowing in at state 2 minus the EF of the refrigerant flowing out at state 3. So there's what's coming out of the refrigerant. Where is it going? Since we've already calculated the rate of exergy transfer into the air, we'll just use that number. It was calculated to be 0.589 kilowatts. All right, that's what, no, that's right here, 1.317. Let me jump back here. This was 1.317 kilowatts. So what came out of the refrigerant goes either into the air or is being destroyed in the condenser. Okay, so we have the mass flow rate refrigerant, the flow exergies coming in and out, and we just calculated this exergy transfer rate into the air. And then the only thing you need to calculate is this one. So we calculate the rate of exergy destruction in the condenser, and I'm going to put that answer right here, is in the condenser is 0.210 kW. How about the expansion valve? That's even easier. I can write it over here. Do we have what comes out of the fluid stream, m dot refrigerant times EF3 minus EF4, is simply what's destroyed in the expansion valve. Okay, so for the expansion valve, we find that the destruction is 0.182 kW. What I need to do is clean this up. I just have to erase right here and move this over. So this was 0.263, 0.210, 0.182. All those are kilowatts. All right, and then how about the evaporator? Well, since we already calculated what is coming out of the water, that's the 0.589 kilowatts, you can, well, just do a whole control volume around here. So maybe I should do that slowly here. You have the refrigerant going through, it comes in at state 4, exits at state 1, and so it's the mass flow rate of the refrigerant, it's leaving the system by EF1 minus EF4. Okay, where did it but it came from the transfer of exergy out of the water. This is like here, the transfer of exergy from the water, which we calculated. And if it came out of the water, some of it could be destroyed in the evaporator. All right, so we know the flow rates and the flow exergies. We calculated what came out of the water. That was 0.589 kW. And the only unknown is this exergy destruction in the evaporator. All right, so we do an exergy balance and you calculate that. So the destruction in the evaporator is 0.475. So when you sum up not only all the destructions, but also what is transferred into the air, you get a total accounting of the outs plus destruction of 2.447 kW, and that's perfect match. This needs to match the sum of the ins. All right, so those are full exergy accounting, and now we have to devise and evaluate a second law efficiency for the heat pump system. So what you say is my efficiency, my second law efficiency, sometimes I write it like this, eta with, like 2 Roman numeral 2 or something, II. Second law efficiency is what you want over what is cost. Okay, well, what did we want? We wanted a large rate of transfer where? Into the air. And so we wanted it removed from our system in the air. So what was the magnitude of that? That was 1.317 kilowatts. That's what we wanted from the perspective of a second law. And then what did it cost? Well, you could take the total sum of the ins, but I wrote right here that you can view the geothermal heat source as being free, and that you actually really only have to pay for to run the power on the compressor. So let's just do that, divide by 1.85 5, 8, and then you get a second law efficiency of about 71% for this system. Well, that was a long problem, and I hope that there was something useful in it for you. Thank you for your attention.